good afternoon everyone, and thank you for attending the honors presentation of Cadet Virginia Bigelow from the Mechanical Engineering Department. Today Ms. Bigelow is going to discuss her project, which is CFD modeling of a pulse tube cryocooler and microgravity conditions from 4 to 80 Kelvin. As the advisor on the project, I'd like to say I couldn't be more pleased with the work that Ms. Bigelow did. She worked in a very dedicated manner both in the fall and spring semesters, and I think the fruits of her work will be shown here today. So with that being said, I'll turn the floor over. Thank you.
Alright, so as he said, my name is Virginia Bigelow, and I'm going to be working on the computational modeling of a high-frequency pulse tube cryocooler for performance in microgravity conditions from 4 to 80K. My advisor is Lieutenant Colonel Ryan Taylor, and I'd just like to thank the Honors Department, or not Department, Institute Honors, as well as the Mechanical Engineering Department for all the just kind of support I've gotten in getting to this point. So, a general overview. So I'm going to take you through the introduction of a pulse tube, kind of get everybody to understand what a cryocooler is, the objectives for my project, the project methodology, how I got where I got, and the simulation setup, so that's the big chunk of the project, and then post-processing, so how I took the results from my simulation and turned them into viable data, and then my results, and the conclusion. So introduction. So, the history of refrigeration starts obviously with ice. Before 1748, that was really all that there was, it's just varying uses of ice. In 1748, you get the first real refrigerator from Cullen. And then between 1748 and 1946 is the invention of the Stirling engine, which in 1946 was run backwards by the Phillips Company, and they accidentally liquefied air. So by 1947, you've got mass liquefaction of both helium and air entering into the field. And that led to the development just a few years later of the Joule-Thomson cryocooler, which today's application works all the way from small microcooling to the liquefaction of air and helium. And then around the same time, you get all three of these pulse tube cryocoolers. So you get the Stirling cryocooler, the Gifford McMahon, and the pulse tube cryocooler. So the big difference between the other cryocoolers and the pulse tube cryocooler is that in the actual pulse tube, there's not a displacer between the hot and the cold end. It's a gas piston, so it's just a piece of gas that will not move out of the pulse tube. So applications, as I said before, liquefaction of air and helium. Pulse tubes, cryocoolers can also be used terrestrially for the cooling of superconductors for things like MRI machines up here, computers, and then peak shaving. And then mainly what I really wanted to look at, so they have a huge application in the field of cooling infrared sensors. So that's for missiles, surveillance, imaging, and these are two major projects that are happening. TIR's thermal infrared sensor and space-based infrared sensors. And they are going, these are specifically right over Earth, but there are some imaging and more focus of this project are the ones that are moving out into free space. And cryosurgery is also kind of a out there application of pulse tube cryocoolers. So, the ideal pulse tube cryocooler cycle. So this is grand scheme. So we've got a couple components. This is the compressor piston. This is the aftercooler, the regenerator. This is the cold heat exchanger, and this is the gas piston, the piece of gas that's not going to move out of the pulse tube. And then we have the warm heat exchanger, the connection to the volume reservoir, and then a volume reservoir that would be down here. So what happens is that the compressor piston is going to push down, it's going to heat up the air, it's going to raise the pressure to be larger than the system, like the reservoir, and then some of the heat is going to escape through the aftercooler, which is what it's supposed to do, and the rest is going to be held in the regenerator. Now, so the pressure went up, and then what's going to happen at a shifted time scale afterwards is that the flow is going to move down. So the velocity is going to be moving this way, and it's going to kind of expand the cold region, and this piston is going to compress the air on this side, and it's going to lose some heat through the warm heat exchanger. Now, when the compressor piston comes back up, what it's going to happen is because we have a shift between pressure and mass flow, the the gas piston is going to stay in this location, but this section of air is going to get even colder. And at this point, it becomes cold enough to accept the cooling load, so it's going to accept heat from whatever it's trying to cool, thus cooling it. And then the mass is going to start moving back upwards, and eventually the temperature is going to sort itself out back to ambient, so the pressure will again equal the pressure of the reservoir back at stage 1. So, objectives. So the purpose of this project, this is a figure that is showing the losses in the pulse tube cryocooler in general. So this is the component that we really want to look at. So at 4 Kelvin, which is a 30 hertz case, the pulse tube cryocooler accounts for a significant amount of losses. Not the most, but if you would go ahead and look at 80K, which is a 60 hertz case, the pulse tube is responsible for more losses. So this warranted separating the pulse tube component from the pulse tube cryocooler in order to optimize it and really do some computational research about how to optimize it and isolate what losses are inherent to the pulse tube. And by optimizing it, we hope that when we put it back in the pulse tube cryocooler and start adding pieces, that it would become a more optimized system. So objectives. So I want to isolate and idealize the pulse tube component of the pulse tube cryocooler for microgravity conditions. So in cooling infrared sensors, we'd kind of be working with either 4 to 20 Kelvin, which will be a 30 hertz case, so that's the frequency it'll be operating at, or 30 to 80 Kelvin. And we're going to maximize the pulse tube based off of 4 really main components, and that's the actual geometry of the pulse tube, the length and diameter, the aspect ratio, which is the ratio of length to diameter, so changing the way the pulse tube is shaped a bit, the pressure ratio, the mass flow rate at the inlet of the pulse tube, and we're going to accomplish this doing pulse tubes with and without a physical wall. We do that so that we can isolate the actual losses coming from the flow, and then by adding the physical wall, we have a baseline to see what losses are coming from just the wall. And then these are done using computational models created in ANSYS Fluent, and the post-processing was done in MATLAB. So project methodology. So the way that this project is done is we first did some pre-processing, which includes optimizing the pulse tube size before we even get to simulations, based off of the simulations that we want to run, and then once we have the pulse tube size, we're going to take the geometry and we're going to import it into, we're going to create an actual 2D geometry in what's called ANSYS geometry, and then we're going to mesh it, which I'll explain a little later, and then put it into ANSYS Fluent, which I'll also explain later. But it just kind of shows how we're going to do this and then get to the MATLAB results, which look like this. They take the data found in Fluent and turn it into usable results. So optimization of the pulse tube size. So we want to really mitigate losses in the pulse tube, which means we want laminar flow. So it's going to be smooth flow through the pulse tube instead of turbulent, which is like chaotic flow. And we do this based off of a critical Reynolds number, which was found using the Stokes oscillatory boundary layer from a previous study that I looked at, and it's cited right there. So this is a critical Reynolds number specifically for the pulse tube that really, because the turbulence is oscillatory in nature in the pulse tube, so it keeps the flow laminar. And then, so how this starts is we start with this equation right here, and we're going to try to optimize, and that gives you the optimal volume of the pulse tube based off the mass flow rate at the inlet, the cold mass flow rate, the angular frequency, which is found using the operating frequency of the pulse tube, and the density at the cold end. So the optimal volume is going to be changing based off of cold temperature and operating pressure. And then we use the thermal penetration depth. That was the thermal penetration depth mentioned up here. And we use dynamic viscosity and angular frequency to find that value. And then we use that and apply a safety factor. So the critical Reynolds number is a do not cross number if we want to stay laminar in flow. So we assigned a safety factor of 2 so that we could stay within laminar flow. And we calculate the area minimum, which you can find the diameter. And then we have a volume ratio. So volume ratio, we want it to be between 3 and 15. So it's a ratio between the optimal volume that we calculated and the actual volume of the pulse tube that we're going to model. So we want to make it a little bigger so that we can see what's happening inside the pulse tube. But obviously for space applications, we want it to be on the smaller side. So we chose a volume ratio of 5. And then the aspect ratio of length to diameter, was either going to be 4 or 8. And that backs out the diameter and length that we need. Now, the diameter and length that we got are very specific values, and they're obviously not so easy to manufacture. So what we did is we bumped those values up to the next manufacturable length and diameter. Now, the thing about this is it did raise the volume ratio, so now the volume ratio is sitting in between 5 and 15. We had one case at 15, but most of them are around 7, which is still pretty good. So this chart is basically just showing you that we ended up with 12 different pulse tubes, and they change based off low temperature, aspect ratio, inlet flow rate. And these 12 pulse tubes were each used 4 times, and I'll explain that in a bit later. So the next step, kind of pre-processing, setting up before Fluent, is meshing. So meshing is when you take a geometry that you've built and you cut it up into a bunch of little tiny pieces, and for each of these tiny pieces, you're going to solve the energy equation, the continuity equation, the x and y velocity equation, so that it all balances out to 0 in one of those little things. So for this, the smallest one that we had was about 0.02 inches squared, and that was kind of based off the thermal penetration depth. And the reason that we did 2D is the way that we modeled it in Fluent was an axisymmetric model, so that's our axis of symmetry, and it's going to rotate all the way around, thus basically solving a 3-dimensional model of the pulse tube. So, but with way less time, so it's going to take far less computational hours. And as we mentioned earlier, we modeled with and without a physical wall. The thickness of the wall was always 0.01 inches. This was based off data that said, on a previous paper that said 3 millimeters was a pretty optimal wall size. So 0.01 is similar to that. And we had a total of around 2,400 elements, so less than that number. And the reason that the mesh is so small in this area is to account for all the effects of the flow that happen near the wall. So meshing convergence, if your elements are too big, you will not be able to account for everything that's happening within the pulse tube. So meshing convergence is when you account for the number, you create a bunch of different meshes, and you run them through the same simulation to see if your mesh gives you the same kind of results as the meshes with lesser elements. So if I were to show you a graph with even fewer elements, it would kind of trend upward like that. And this is just showing you the branch that means that the mesh that we used at 2,400 elements was converged. So it just kind of validates the model that we used. And we did it based off cycle 2 energy error. So simulation setup. So this is the overall grand scheme of what we did, over 10,000 computational hours on the computer. And this just kind of to help you understand like the scope of this project. So we did a no-wall model at different temperatures with different pressure ratios, different aspect ratios, and then mass flow at the inlet, all 3 of them. In addition to this, we ran an additional, so this is total 48 cases. We ran an additional 16 because in reality you can't really have a perfect pulse tube for every case that you want to run. So what we did is we took the pulse tube optimized for these cases and ran them at 3 and 1, and we'll show that data later as well. So Fluent simulation setup. So the flow velocity is very small. So low Mach number, low Reynolds number. We made sure that the flow was going to stay laminar by optimizing the pulse tube size. So we can model laminar flow, real gas, and it's a pressure-based flow. So this is a transient solution. So what that means is basically we have an operating frequency, which is going to give you the period of 1 cycle. And so what we want to do is create a small time step so that it's solving within that period. So we took the period and we divided it by 400. So it solves that 400, and that's just one cycle. So we solved it 400 time steps, 75 times. So that's why, you know, you end up with 10,000 computational hours. So we also modeled at 2 different operating pressures, and this is just based on the relationship between your pressure amplitude and mean pressure. So that's where the pressure ratio comes in. And 30 and 60 hertz for the 4 to 20 and 30 to 80 cases. And then to speed up solving, we came up with a custom temperature function that when the simulation starts, sets this side at 4, sets this side at 20 or 30 to 80, and then kind of breaks apart the pulse tube so it's faster to solve. And then we had data exported at 5 different locations for every time step that we solved. And we've got some that are like slightly in from the inlet because we wanted to account for any effects that were happening right at the inlet or the exit, and then one right in the middle. So fluid and wall conditions. So we used real gas, and this chart over here is kind of why we had to use real gas. So compressibility factor is the ratio between molar volume of helium and the ideal molar volume of helium. So if it's not 1, then you need to use real gas. You can see between 4 and 20 K, the need for real gas was 100% there. And then for the 30 to 80 K, the 2 megapascals is consistently sitting above 1, so it justified using real gas for the models. And then the wall, we used stainless steel. And the way that we found properties for the wall is we used a curve fit in engineering equation solvers, so ease, and found these values for both 4 to 20 and 30 to 80 for the wall properties such as specific heat, density, and conductivity. And we inputted them in Fluent using basically their equivalent with the curve fit. So boundary conditions. For Fluent, this is kind of the most important piece. It's setting up what happens in the pulse tube. So we use C files, which is coding, to basically set the frequency, mass flow inlet, and what happens at the pressure outlet. So this is a mass flow inlet, and that's a pressure outlet, and they were set using C files. As I mentioned before, this is the axis of rotation. And then this thickness of the wall right here was set to the low end temperature, and the one over there was set to the high. The interface between the wall and the fluid is just a coupled solver, which means there's no extra heat being added there. It's just going to compute the relation that happens between the wall and the fluid. And then to model an insulated wall, we set this as a heat flux and then set the heat flux to 0. So no heat is traveling from the outer side inward to the pulse tube, so that we could really isolate the losses that are coming from the wall and the wall only, so not from the outside air. So post-processing. Post-processing starts in Fluent as well. So this is what you see while your simulation runs for hours and hours and hours. And what this shows is, so within a time step, so even smaller, so we have cycles, and then we broke the cycles down into time steps. Within each time step, you're going to run 30 to 40 iterations. And all this shows you is that one iteration is just the solution of all your continuity and energy equations is the one solution, and then the next one are no different than 1e to the -4th. So it's just showing you that over time, the differences between iterations and the solutions are getting even smaller. So these are the 4 different things that it's solving for, and as it goes, it just shows that it's converged between time steps. And then overall, so in the cycles, we did an energy error sum. So the values that we solved for were integrated so that we had an average per cycle, and then we show it over cycles. So it shows that it's 0. Some of the later simulations were more of a quasi-steady state, so their energy error would fluctuate up and down 0, kind of like that. But it's still considered steady state for this. Alright, so this is what Fluent kind of produces as far as imagery is concerned. And this just shows you, so this stage is like stage 1 of the pulse tube cryocooler, where piston's pushing down, the mass flow hasn't really happened yet, the velocity is kind of sitting in the middle, and then you get a higher push this way, you get that expansion of the cold, and then as the piston moves back up, you get velocity flowing back the other direction, and your cold is going to expand even more so that it can accept the cooling load, and then it's going to heat back up from that cooling load, and then the mass flow rate is going to push the piston back to the other side. So as you can see, this area of the pulse tube never leaves the pulse tube, and that's what basically your gas piston is. Now this was from our most efficient case. These are images from our most efficient case, and compared to our lowest efficient case, you can see that the velocity flow is much lower, and the flow is a little bit more unstable. You see heat starting to push into the gas piston from the hot side, and these are on the same scale, so you can definitely see that one is a little more straight than the next. As well, as we would expect, the lowest efficiency case was one with a wall, whereas this one was without a wall. And you can see how the temperature of the wall changes kind of slowly compared to the temperature of the fluid. It's not quite the same, and that's where your wall losses come from. So these are the basic main equations that we have for the post-processing. So all of our values are time integrated. And then this is going to be your cooling power. So this is the first thing that we look at. And it's going to be the enthalpy, the time averaged enthalpy, including the losses. So these are going to come out negative from fluid. And these are going to be the losses associated with the wall and then the gas itself. As you can see from this image, like these are losses. And then figure of merit, which is kind of a way to measure the efficiency of the pulse tube component specifically, and it's going to be this enthalpy minus the losses that we have over the ideal, just the ideal refrigeration of the pulse tube. So this is just kind of an example of what post-processing looks like. As you can imagine, we had 48 simulations, so we had a lot of these graphs floating around. And this is kind of what the energy area shows, and this is the PV. So you can see it's always going to be higher than the value over here. And this is going to be the inlet and the exit of the pulse tube. So very small differences. It's a pretty highly efficient pulse tube, and these numbers are very similar to the one over here. So the way we did this is data files were created in Fluent while it solves, and then exported into MATLAB, and like I said, they're average time integrated values, and they'll help us solve for the equations on this slide right here. So results. So this graph's a little busy, so I'm going to break it down a few bits. So this is the figure of merit on this side. You can see the range is not very large. These are all very high efficiency cases because we've tried to idealize it and mitigate as many losses as possible so that we can really see the trends between the cases that we evaluated. And these are the no-wall cases. So this kind of breaks it down for anybody who wants to know whether, so say they need to run a 4-aspect ratio pulse tube and they want to operate at 60 hertz, what the trends are going to look like in there. So you can see within each set there are established trends, some of them different than others, but there are definitely strong trends. Usually, with the exception of like this area over here, the 1 gram per second mass flow rate at the inlet operates at a lower efficiency than the 3 and 5. And then we've got for the wall cases, if you look at the scale, we can see we're starting to lose a lot more. From 0.91 to 0.99, we've got something as low as in the 0.75 region. But this is just the same kind of concept. You can still see some noticeable trends in most of them. Some of them were because the volume ratio was a little higher than others, but yeah, still mostly noticeable trends, just generally lower than the no physical wall cases. So this was the study that I was talking about where we took the pulse tube that was optimized for the 5 gram per second inlet and ran it at both 1 and 3, and this shows how they operated. So in general, it kind of showed that if you wanted to run at a mass flow rate slightly lower or potentially maybe even higher. It's going to stay kind of around, the red and the green are generally pretty close, or at least not crazy less optimal. So